Hello there. I'm so glad you found your way here tonight. Right now, as you settle in, something remarkable is happening far above you. Beyond the clouds, beyond the blue sky, beyond the thin veil of atmosphere that keeps us safe, an infinite ocean of stars is quietly turning. Spacecraft are orbiting the Earth at this very moment, carrying astronauts who watch the sunrise 16 times a day. Every rocket launch, every spacewalk, every moment of silence in the void carries within it a story of human courage and curiosity. Space is not a place we visit. It is a place that has always surrounded us. It stretches in every direction, patient and endless, waiting for those brave enough to explore it. Tonight, we journey into the quiet world of space travel. We will explore over 100 soothing facts about the cosmos, from the strange sensation of floating in zero gravity, to the haunting silence of the vacuum, from the first footprints on the moon, to the distant dream of walking on Mars. There is no test at the end, no rush, no urgency. Just the gentle unfolding of the universe to carry you softly towards sleep. So let your breathing slow. Let your thoughts grow quiet, and allow yourself to drift into the peaceful wonder of the stars above. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the remarkable journeys happening beyond our atmosphere. Either way, this space is for you. There is something deeply calming about contemplating the vastness of the cosmos. Every rocket, every satellite, every quiet moment of an astronaut gazing back at Earth carries within it a story millions of miles in the making. You are part of that story. The same atoms that form your body were once forged in the hearts of ancient stars. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was created in stellar furnaces billions of years ago. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. So settle in. Let the weight of the day drift away. And let us begin with the first of many quiet truths about space travel. Space travel is patient beyond measure. Missions take years to plan. Spacecraft travel for months or years to reach their destinations. Astronauts train for decades before they ever leave Earth. And yet, within all that slowness, there are sudden bursts of wonder. Rockets that thunder into the sky in moments. Sunrises that paint the Earth in gold every 45 minutes. First steps on alien soil that change history in a single heartbeat. Tonight we will wander through this magnificent realm. We will meet the brave souls who float among the stars. We will discover the strange beauty of life without gravity. And we will uncover truths about space that may surprise even the most curious minds. But there is no hurry. The universe has been expanding since the beginning of time. It can continue its quiet dance while you rest. Let us begin with what space travel truly means. A spacesuit is a personal spacecraft wrapped around your body. When an astronaut steps outside a spacecraft, they are essentially becoming their own little spaceship. A spacesuit is far more than protective clothing. It is a complete life support system designed to keep a human alive in the most hostile environment imaginable. The suit provides oxygen to breathe, removes carbon dioxide from exhaled air, regulates body temperature in extreme heat and cold, and protects against the vacuum of space. It shields the wearer from harmful radiation streaming from the sun, and from tiny micrometeoroids that could puncture ordinary fabric. Layers of advanced materials work together to maintain air pressure against the skin, preventing bodily fluids from boiling in the vacuum. Communication systems built into the helmet allow astronauts to speak with their crewmates and mission control back on Earth. Every spacesuit is a marvel of engineering, containing hundreds of components that must work flawlessly to keep the astronaut alive. The cost of developing and testing modern spacesuits can exceed many millions of dollars, reflecting the extraordinary complexity required to keep a human safe in the void. Astronauts grow taller in space. Without the constant downward pull of gravity, the human body stretches in surprising ways. On Earth, the weight of your upper body compresses the discs between your spinal vertebrae throughout the day. In microgravity, this pressure is relieved, allowing the discs to expand and the spine to straighten. Astronauts can gain up to 5 centimeters in height during their time in orbit. This extra height is temporary, however, as the spine compresses again once the astronaut returns to Earth's gravitational embrace. The stretching can sometimes cause back pain, as muscles and ligaments adjust to the new spinal length. Scientists study this phenomenon carefully, because understanding spinal health in space helps prepare for longer missions to the Moon or Mars. Medical monitoring includes regular measurements of height and scans to observe how each vertebra responds to weightlessness. The body's elastic response to weightlessness is a fascinating reminder of how deeply gravity shapes our everyday existence. Space smells like burnt steak and hot metal. Astronauts who return from spacewalks often describe a distinctive and unexpected odor clinging to their suits and equipment. They compare the scent to burnt steak, seared meat, hot metal, or even gunpowder. Scientists believe this smell comes from dying stars, where high-energy particles create compounds called polycyclic aromatic hydrocarbons. These molecules drift through space and can settle on spacecraft surfaces. When astronauts bring their suits back into the pressurized environment of the station, the residue produces that characteristic odor. Some describe it as sweet and metallic, while others find it acrid and smoky. Interestingly, efforts have been made to recreate this scent on Earth, so that curious minds can experience a hint of the cosmos without leaving the ground. The smell of space is not something that can be experienced directly, since opening one's helmet in the vacuum would mean instant death. Instead, astronauts catch only faint traces carried on objects that have been exposed to the void. This strange cosmic perfume remains one of the more unexpected sensory experiences of space travel. Bones lose density faster in space than on Earth. The human skeleton is designed to support the body against gravity. When that constant stress is removed in microgravity, bones begin to weaken at an alarming rate. Astronauts can lose about 1 to 2% of their bone mass each month while in orbit, particularly in the hips, spine, and legs. On Earth, bone loss at this rate would take years. In space, it happens in weeks. The body essentially decides it no longer needs such strong bones, and calcium leaches from the skeleton into the bloodstream. This poses serious risks for long-duration missions, as weakened bones can fracture more easily upon return to gravity. Exercise regimens on the International Space Station help slow this loss, but they cannot prevent it entirely. Researchers continue to study new medications and supplements that might help astronauts maintain bone health during extended voyages. Returning astronauts often require months of rehabilitation before their bones regain enough strength for everyday activities. The sun looks white in space, not yellow. From Earth's surface, the sun often appears yellow or orange, especially near sunrise or sunset. This is because Earth's atmosphere scatters the shorter blue wavelengths of light, letting the longer yellow and red wavelengths dominate our view. In space, there is no atmosphere to filter sunlight, so astronauts see the sun as it truly is, a brilliant white orb. The sun emits light across the entire visible spectrum, and when all those colors reach your eyes together without interference, they blend into pure white. This intense, unfiltered light is one of the reasons astronauts wear visors coated with gold to protect their vision. The clarity of sunlight in space is so powerful that it can illuminate spacecraft interiors with dazzling brightness. Long exposure to this unfiltered glare can cause serious eye damage without proper protection. Looking at the sun's true color reminds us that so much of what we perceive on Earth is shaped by the thin blanket of air surrounding our planet. Food in space must be designed for zero gravity. Eating in space presents unique challenges that require careful planning and engineering. In microgravity, crumbs and liquids do not fall to the floor. They float freely through the cabin, potentially clogging air vents or getting into equipment. Space food is therefore designed to minimize loose particles and to stick together well. Meals are often freeze-dried, thermostabilized, or packaged in pouches that can be rehydrated with water. Astronauts use tortillas instead of bread because tortillas produce fewer crumbs. Drinks come in sealed containers with straws to prevent liquid globules from escaping. Despite these constraints, space agencies work hard to make food tasty and nutritious, understanding that morale depends partly on enjoyable meals. Astronauts have enjoyed everything from shrimp cocktail to chocolate pudding in orbit. Some crews have even baked cookies in specially designed ovens as experiments in space cuisine. The science of space food has improved significantly since the early days of space travel, when meals were squeezed from tubes like toothpaste. Astronauts sleep in strapped cocoons on walls. Sleep in microgravity requires a completely different approach from resting on a bed at home. Without gravity pulling the body down, astronauts would drift aimlessly through the cabin if they simply closed their eyes. Instead, they slip into sleeping bags attached to walls or other surfaces inside small compartments. The bags have straps and clips that keep the sleeper in place throughout the night. Some astronauts strap their arms down so they do not float up and bump into things. Ventilation is essential because exhaled carbon dioxide would otherwise form a bubble around the face and cause suffocation. Despite these precautions, many astronauts report that sleeping in space feels wonderfully restful, like floating on a soft cloud. Some even describe vivid dreams inspired by their unique surroundings among the stars. The absence of pressure points means there is no tossing and turning to get comfortable. Adjusting to this new way of sleeping typically takes a few days, after which many find it deeply peaceful. Tears do not fall in space, but form floating spheres. Crying in microgravity is a strangely beautiful, yet uncomfortable experience. When tears form in space, they do not roll down the cheeks as they would on Earth. Instead, the liquid pools around the eyes and clings to the surface of the skin due to surface tension. If more tears are produced, they gather into wobbling, spherical blobs that eventually break free and drift through the cabin. Astronauts who have wept in space describe the sensation as stinging and irritating because the tears accumulate rather than draining away. Some have had to use towels to dab away the collected liquid. The floating teardrops themselves are oddly beautiful, glistening spheres suspended in mid-air. Videos captured aboard the International Space Station have shown these remarkable liquid orbs for audiences back on Earth. This phenomenon is a reminder that even the simplest human actions, like crying, become novel experiences in the absence of gravity. Emotions travel with us beyond Earth, but their physical expressions take on new and unexpected forms. A single spacewalk can last over 8 hours. Spacewalks, formerly called extravehicular activities, are among the most physically and mentally demanding tasks astronauts perform. Preparing for a spacewalk takes hours, including time to put on the spacesuit and pre-breathe pure oxygen to prevent decompression sickness. Once outside, astronauts may work for 6 to 8 hours or even longer on complex repairs and assembly tasks. Throughout this time, they must carefully manage their oxygen supply, temperature regulation, and hydration through drinking water pouches inside their helmets. Many spacewalks push astronauts to their physical limits, leaving them exhausted but exhilarated. The thick gloves that protect their hands also make fine motor work incredibly difficult, turning simple tasks like turning a bolt into laborious efforts. Communication with mission control is constant, as every action must be coordinated precisely. Despite the difficulty, astronauts describe spacewalks as profoundly moving experiences, floating above Earth with the stars surrounding them in every direction. There is no up or down in orbit. In the weightless environment of orbital flight, the concepts of up and down lose all meaning. On Earth, gravity provides a constant reference. The ground is down, the sky is up. In space, astronauts can orient themselves in any direction, and it feels equally natural. One person's ceiling is another's floor, depending entirely on how they position their body. This freedom can be disorienting at first, as the brain struggles to process an environment without gravitational cues. Designers of spacecraft interiors often use color coding and visual markers to help astronauts maintain a consistent sense of orientation. Some modules have specific walls designated as floors, simply for practical organization. Veteran astronauts often enjoy playful photographs of themselves eating dinner on what would normally be the ceiling. Over time, astronauts adapt remarkably well, using handholds and footholds to move gracefully through their three-dimensional world. The experience of living without up or down is one of the most alien aspects of space, challenging our deeply ingrained understanding of physical reality. Cosmic radiation can rewrite parts of your DNA. Beyond the protective shield of Earth's atmosphere and magnetic field, astronauts are exposed to higher levels of cosmic radiation. These energetic particles, originating from the Sun and distant galaxies, can penetrate spacecraft walls and human tissue. When cosmic rays pass through living cells, they can damage DNA strands, potentially causing mutations. Most of these mutations are harmless or repaired by the body's natural mechanisms, but some can increase the risk of cancer and other health issues. Extended missions beyond low Earth orbit, such as journeys to Mars, would expose astronauts to significantly higher radiation doses over months or years of travel. Scientists are developing better shielding materials and studying medications that might help protect against radiation damage. Monitoring systems aboard spacecraft track cumulative exposure so that astronauts do not exceed safe limits. Some research even suggests that certain genetic changes observed in astronauts persist long after they return to Earth. Understanding and mitigating radiation risks is one of the biggest challenges facing future deep space exploration. Fire burns differently in space, forming blue spheres. Flames on Earth are shaped by gravity, which causes hot gases to rise and creates the familiar teardrop shape of a candle flame. In microgravity, there is no convection to draw oxygen to the flame and carry away combustion products. As a result, flames in space burn in nearly perfect spheres. These spherical flames tend to be smaller, cooler, and often blue in color because they burn more efficiently with less soot. Scientists conduct combustion experiments on the International Space Station to better understand fire behavior in weightlessness. This research has practical applications for spacecraft safety, helping engineers design better fire detection and suppression systems. Understanding how flames behave differently in microgravity has also led to insights that improve fuel efficiency and combustion engines on Earth. Watching a flame hover in mid-air as a glowing orb is both beautiful and eerie. The study of fire in space also provides unexpected insights into combustion processes that can improve technology far from orbit. Astronauts must exercise for over 2 hours every day. Maintaining physical fitness in space requires dedicated effort because the body begins to deteriorate without the constant stress of gravity. Astronauts on the International Space Station follow rigorous exercise programs lasting more than 2 hours each day. They use specially designed equipment, including treadmills with harnesses that strap them down, and resistance machines that simulate weightlifting. Without this exercise, muscles would atrophy and bones would weaken at dangerous rates. Even with intensive workouts, astronauts still experience some loss of muscle mass and bone density. The exercise sessions also serve a psychological purpose, providing routine and helping to relieve stress after demanding work schedules. Space Agency scientists continue to develop new exercise protocols and equipment to maximize the benefits while minimizing the time required. Returning astronauts often describe feeling unexpectedly heavy as their weakened bodies readjust to Earth's gravity. The importance of exercise on future long-duration missions to the Moon and Mars cannot be overstated, as crew health is paramount to mission success. Two pieces of metal can fuse together instantly in space. In the vacuum of space, a phenomenon called cold welding can occur when two pieces of similar metal come into contact. On Earth, thin layers of oxide and contaminants coat metal surfaces, preventing this bonding. In the vacuum, these protective layers are absent, so when clean metal surfaces touch, their atoms can diffuse across the interface and fuse together permanently. Engineers must carefully select materials and coatings to prevent spacecraft components from accidentally welding together during assembly or operation. Moving parts like hinges and mechanisms require special lubricants that remain effective in vacuum conditions. Cold welding was first observed in early satellite missions and has since become a well-understood hazard that mission designers account for in every project. Despite being a potential problem, this phenomenon has also inspired research into new bonding techniques that could be useful for space-based construction. Understanding cold welding helps ensure that spacecraft mechanisms continue to function properly throughout their missions. Food tastes different in microgravity. Astronauts often notice that food seems blander and less flavorful in space than it does on Earth. This change is partly due to fluid redistribution in the body. Without gravity pulling fluids downward, blood and other liquids shift toward the head, causing congestion similar to having a cold. Blocked sinuses reduce the sense of smell, which is closely linked to taste. Many astronauts develop a preference for spicy and strongly flavored foods to compensate for this dulled palate. Space agencies take these changes into account when designing menus for long-duration missions, often including extra condiments and flavorful options. Hot sauce and other condiments are popular items on the International Space Station. Fresh foods, when available on resupply missions, provide a welcome burst of flavor and texture that packaged items cannot match. Over time, some astronauts report that their sense of taste adapts, though it never fully returns to normal until they land. The subtle ways microgravity affects our senses are yet another reminder of how finely tuned our bodies are to life on Earth. Almost every astronaut experiences space sickness. Within the first few days of arriving in orbit, the majority of astronauts experience some form of space motion sickness. The condition is caused by conflicting signals from the inner ear, eyes, and muscles as the brain tries to make sense of a gravity-free environment. Symptoms can include nausea, disorientation, headaches, and vomiting. For some astronauts, the sickness is mild and passes quickly. For others, it can be severe enough to affect their ability to work. Medications can help manage symptoms, and most crew members adapt within a few days as their brains recalibrate to the new sensory inputs. Experienced astronauts learn to move slowly and avoid sudden head movements during the adjustment period. Space agencies carefully monitor new arrivals and schedule lighter duties until they have acclimatized. Long-term research aims to better predict who will suffer severe symptoms and develop improved preventive treatments. Understanding and managing space sickness is crucial for mission success, especially during critical early operations. Shooting stars can happen inside a spacecraft. Astronauts sometimes report seeing brief flashes of light, even with their eyes closed, especially when trying to sleep. These flashes are not shooting stars in the traditional sense, but they are caused by a similar phenomenon. High-energy cosmic ray particles occasionally pass through the spacecraft and interact with the fluid inside the eye, or directly with the retina. When these particles strike the visual system, they produce bursts of light that the brain interprets as flashes, streaks, or patterns. Scientists call these visual disturbances phosphenes. The effect is more common during missions beyond low Earth orbit, where cosmic radiation levels are higher. While generally harmless in the short term, frequent exposure raises concerns about long-term eye and brain health on deep space missions. Studying these events helps researchers understand the effects of cosmic radiation on the human nervous system and develop protective countermeasures for future exploration. Plants can be grown in space without soil. Growing food in space is essential for long-duration missions beyond Earth orbit. Scientists have successfully cultivated plants aboard the International Space Station using hydroponic and aeroponic systems that deliver nutrients directly to the roots without soil. These methods allow precise control over growing conditions and are more efficient in the confined environment of a spacecraft. Lettuce, radishes, peppers, and other crops have been harvested and eaten by astronauts in orbit. Beyond providing fresh food, plants also contribute to crew morale and mental well-being. The presence of green, living things helps astronauts feel more connected to Earth during long months away from home. Plants can also help recycle air by absorbing carbon dioxide and releasing oxygen. Research continues to develop larger and more productive growing systems that could eventually sustain crews on journeys to Mars and beyond. Blood moves differently in zero gravity. On Earth, gravity helps distribute blood throughout the body, pulling it downward toward the legs and feet. In microgravity, this effect disappears, and blood redistributes toward the upper body and head. Astronauts often develop puffy faces and thinner legs within hours of reaching orbit, a condition informally known as chicken legs and puffy face. The heart, accustomed to pumping against gravity, begins to change shape and becomes slightly weaker over time. Blood volume also decreases as the body adjusts to the new fluid balance. These cardiovascular changes can affect vision, with some astronauts experiencing permanent alterations to their eyesight after long missions. Researchers are studying these effects closely because maintaining heart health is critical for long-duration missions to the Moon, Mars, and beyond. Upon returning to Earth, astronauts may feel dizzy or faint as their cardiovascular systems readapt to gravity. Spacecraft are surprisingly loud inside. While space itself is silent, the interior of a spacecraft is filled with a constant background hum. Fans circulating air, pumps moving coolant, life support systems filtering atmosphere, and computers generating heat all contribute to a noisy environment. On the International Space Station, sound levels can reach those of a busy office or city street during peak activity periods. Astronauts often wear earplugs while sleeping to get adequate rest. Prolonged exposure to this noise can cause hearing damage if not managed carefully over months of living aboard. Engineers work to reduce noise levels and isolate vibrating equipment, but some sound is unavoidable given the machinery required to sustain life. The persistent background noise becomes so familiar that returning astronauts sometimes find Earth strangely quiet by comparison. Learning to sleep through the mechanical symphony of a living spacecraft is one of many adjustments astronauts must make. Viruses can become stronger in space. Research conducted in microgravity has revealed that some microorganisms, including viruses and bacteria, can become more virulent in space. The stress of the space environment triggers changes in gene expression that can make pathogens more aggressive and harder to kill. Studies with Salmonella bacteria showed increased virulence and resistance to certain treatments when grown aboard the space shuttle. This poses concerns for long-duration missions, where crew members live in close quarters with limited medical resources. Understanding how pathogens behave differently in space helps researchers develop better countermeasures and more effective treatments. Some experiments suggest that the same microgravity conditions that strengthen pathogens might also weaken the human immune system, creating a compounding challenge. This double challenge requires careful attention to hygiene, health monitoring, and medication stocks on future missions. Scientists are exploring ways to use this knowledge to create new vaccines and therapies. Surprisingly, studying disease in space has also led to insights that could improve treatments on Earth. Astronauts wash with floating water globes. Personal hygiene in microgravity requires creative solutions, since water behaves very differently without gravity. When released from a container, water forms floating spheres that wobble and drift through the air. Astronauts use dampened washcloths and carefully squeezed water droplets to clean themselves. They apply no-rinse soap and shampoo, wiping it away rather than rinsing under a shower. The floating water globes must be captured quickly before they float into equipment or air vents. Watching astronauts chase water droplets with a towel has become a popular sight in space station videos shared online for educational outreach. Despite the challenges, astronauts report feeling surprisingly clean after their adapted bathing routines. The process takes longer than showering on Earth, but becomes second nature with practice after a few weeks in orbit. Managing water carefully is essential because every liter must be recycled and purified for reuse. Moon dust is more dangerous than it looks. The fine gray powder covering the lunar surface may appear harmless, but it poses serious risks to astronauts and equipment. Lunar regolith, as the dust is called, is composed of tiny, jagged particles created by billions of years of micrometeorite impacts. Unlike dust on Earth, which is rounded by wind and water erosion, moon dust is sharp enough to scratch visors and damage seals. During the Apollo missions, astronauts found that dust clung to everything due to static electricity and was nearly impossible to remove completely. Inhaling this abrasive material could cause lung damage, similar to silicosis. The dust also wore through layers of spacesuit fabric within hours of extended exposure. Future lunar missions will need advanced dust mitigation strategies, including special coatings, airlocks with brushing systems, and possibly electrostatic cleaning methods. Research is ongoing to develop fabrics and materials that resist dust adhesion. Understanding moon dust hazards is essential for establishing any long-term presence on the lunar surface. Haircuts in space use vacuum tubes. Maintaining personal grooming in microgravity presents unique challenges that require inventive solutions. When astronauts need a haircut, they cannot simply let the clippings fall to the floor. Instead, hair trimmings are captured using a vacuum hose attached to the clippers. As the hair is cut, it is immediately sucked into the vacuum system, preventing loose strands from floating through the cabin. Without this precaution, tiny hair particles would drift everywhere, potentially getting into eyes, mouths, and sensitive equipment. Crew members take turns cutting each other's hair, a process that requires patience and a steady hand. Some astronauts opt to shave their heads before missions to simplify the grooming process entirely. The adapted barbering technique has become just another routine skill astronauts master during their missions. Watching haircuts happen in space, with the vacuum tube hovering nearby, is a charming reminder of how everyday activities transform beyond Earth. Even mundane tasks become small adventures when gravity is no longer present. Spacesuit gloves are the hardest part to move. Of all the components in a spacesuit, the gloves present the greatest challenge for astronauts. The gloves must be flexible enough to allow delicate manipulation of tools and equipment, while remaining strong enough to protect against vacuum, temperature extremes, and micrometeoroids. When a suit is pressurized, the gloves inflate like balloons, making it extremely difficult to bend fingers and grip objects with precision. Astronauts describe the sensation as trying to work while wearing thick boxing gloves. After long spacewalks, crew members often have sore, blistered hands from the constant effort of fighting against the suit's internal pressure. Engineers continually refine glove designs to improve dexterity without sacrificing protection. Some astronauts have lost fingernails due to the pressure and friction inside the gloves during extended work. New thermal liner designs and improved joint articulation are areas of active research. Despite decades of development, creating the perfect spacesuit glove remains one of the most difficult engineering challenges in human spaceflight. Astronauts have lost tools that became orbiting satellites. During spacewalks, astronauts sometimes lose grip on tools and equipment, despite careful precautions. Once an object drifts away in orbit, it becomes space debris that can circle the Earth for years or even decades. A famous example occurred when an astronaut lost a tool bag during a repair mission, and the bag was visible from Earth through binoculars for months afterward. These floating objects travel at tremendous speeds and pose collision risks to spacecraft and other satellites. Even something as small as a dropped bolt can cause serious damage if it strikes a vehicle at orbital velocities exceeding 20,000 kilometers per hour. NASA and other agencies track as much debris as possible to maneuver spacecraft out of harm's way. The accumulating cloud of space junk is a growing concern for future missions. Each lost item adds to the problem, making debris management an increasingly important aspect of space operations. You cannot breathe on Mars without technology. The Martian atmosphere is utterly inhospitable to unprotected human life. It consists of about 96% carbon dioxide, with only trace amounts of oxygen. The atmospheric pressure on Mars is less than 1% of Earth's sea level pressure, far too low for human survival. Without a sealed spacesuit or habitat, an astronaut's lungs would be unable to function, and bodily fluids would begin to boil in the near vacuum. Temperatures on Mars can plunge to -100 degrees Celsius or colder at night. Any human presence on the red planet will require sophisticated life support systems to provide breathable air, regulate temperature, and maintain proper pressure. Scientists are developing technologies that could extract oxygen from the Martian carbon dioxide atmosphere, or from water ice buried beneath the surface. The MOXIE experiment on the Perseverance rover has already demonstrated this technology on a small scale. Breathing on Mars will always depend on engineering ingenuity and redundant safety systems. Future Mars missions may be one-way journeys. Some proposals for human Mars missions have considered the possibility of sending colonists who would never return to Earth. A one-way trip would drastically reduce mission complexity by eliminating the need for return vehicles, fuel, and supplies for the homeward journey. Early settlers would focus entirely on building a sustainable colony, rather than preparing for departure. Such a mission raises profound ethical and psychological questions about what it means to leave Earth forever. Volunteers would need to accept that they will spend the rest of their lives on another planet, never again experiencing blue skies, oceans, or the company of most of humanity. Supporters argue that one-way missions are how human expansion has always worked, from ancient migrations to colonial settlements across oceans. Critics worry about the isolation, health risks, and moral implications of stranding people so far from home, with no realistic hope of rescue. The debate continues as space agencies plan for the next chapter of human exploration. Rocket fuel is surprisingly inefficient. Despite the thunderous power of a rocket launch, the majority of a rocket's mass is fuel rather than payload. Chemical rockets work by burning propellant at extremely high speeds, but most of that energy is spent simply lifting the fuel itself off the ground. By the time a rocket reaches orbit, it has consumed nearly all its propellant, leaving only a tiny fraction of the original mass as useful cargo. This inefficiency is a fundamental constraint of rocket physics, often described by the tyranny of the rocket equation. Engineers constantly seek ways to improve efficiency, from lightweight materials to more energetic fuels and reusable rocket stages. Alternative propulsion methods like ion engines are far more fuel efficient but produce much less thrust, making them unsuitable for launches from Earth. Until revolutionary new technologies emerge, rockets will remain extraordinarily expensive and wasteful compared to other forms of transport. The search for better propulsion is one of the most important frontiers in aerospace engineering. Space temperatures swing between extreme heat and cold. The thermal environment in space is one of the most challenging aspects of spacecraft design. Objects in direct sunlight can reach temperatures exceeding 100 degrees Celsius, while surfaces in shadow can plunge to -100 degrees or colder. A spacecraft orbiting Earth experiences these extremes roughly every 45 minutes as it passes between day and night. Without careful thermal management, electronics would overheat on the sun-facing side, while freezing on the shadowed side. Engineers design spacecraft with insulation, heaters, radiators, and reflective coatings to maintain stable internal temperatures. Spacesuits must protect astronauts from both blistering heat and intense cold, sometimes within moments of each other. The rapid temperature cycling also causes materials to expand and contract repeatedly, stressing joints and seals over time. Managing thermal extremes is a constant battle throughout every mission. Sunsets on Mars appear blue, not orange. On Earth, we are accustomed to vibrant orange and red sunsets, created as sunlight scatters through our thick atmosphere. Mars presents the opposite effect. The thin Martian atmosphere is filled with fine dust particles that scatter light differently than air molecules on Earth. When the sun dips toward the Martian horizon, blue wavelengths are scattered toward the observer, while redder light scatters away. This creates an eerie blue glow around the setting sun, fading into a pink and brown sky. Photos captured by Mars rovers have shown these alien sunsets in stunning detail. The sight of a blue sunset on a dusty orange landscape is deeply surreal and beautiful. Astronauts who one day stand on Mars will witness this phenomenon firsthand, a gentle reminder that each world has its own unique version of beauty. Space junk is a growing threat to every mission. Tens of thousands of pieces of debris now orbit the Earth, ranging from defunct satellites to tiny paint flecks traveling at tremendous speeds. Even a fragment the size of a marble can strike with the force of a bullet when it is moving at orbital velocities. The International Space Station must occasionally maneuver to avoid tracked debris that could puncture its hull. Smaller pieces are too numerous to track and pose a constant risk during spacewalks and missions. As more satellites are launched each year, the problem continues to worsen. Scientists worry about a scenario called the Kessler syndrome, where cascading collisions create an ever-expanding cloud of fragments that could eventually make certain orbits unusable. Cleaning up space junk is technically challenging and expensive, but several experimental missions are testing removal technologies. The long-term sustainability of space activities depends on addressing this silent and growing hazard. Astronauts train underwater for spacewalks. The closest simulation of microgravity available on Earth is neutral buoyancy, achieved by submerging suited astronauts in giant swimming pools. NASA's Neutral Buoyancy Laboratory contains a massive tank with full-scale replicas of space station modules, where astronauts practice every move they will make during real spacewalks. Divers accompany the astronauts to ensure safety and adjust equipment as needed. Training sessions can last 6 hours or more, mirroring the duration of actual spacewalks. This underwater preparation helps astronauts develop muscle memory for using tools, navigating handholds, and moving efficiently in a spacesuit. The buoyancy of water does not perfectly replicate weightlessness, but it comes remarkably close. By the time astronauts reach orbit, they have rehearsed their tasks dozens of times in the pool. This rigorous preparation is a key reason spacewalks, despite their inherent dangers, are completed safely. Time moves slower in orbit than on Earth. According to Einstein's theory of relativity, time passes at different rates depending on velocity and gravitational fields. Astronauts aboard the International Space Station are traveling at roughly 28,000 kilometers per hour, fast enough for time dilation to become measurable. Their clocks tick slightly slower than identical clocks on Earth's surface. Over a year in orbit, an astronaut ages about 1/100th of a second less than someone who stayed on the ground. The effect is tiny at these speeds, but it is real and has been confirmed by precise atomic clocks flown on satellites. Time dilation would become far more significant on journeys approaching the speed of light, though current technology is nowhere near such velocities. Understanding these relativistic effects is essential for accurate satellite navigation systems like GPS. Space travel brings abstract physics into tangible reality. Cosmic rays can create flashes of light in astronauts' eyes. Beyond Earth's protective magnetic field, astronauts are exposed to heightened levels of cosmic radiation from the Sun and distant galaxies. High-energy particles called cosmic rays can pass through the walls of spacecraft and even through the human body. When these particles interact with the fluid in the eye or strike the retina, they can produce brief flashes of light called phosphenes. Astronauts have described seeing bright streaks, sparks, or glowing spots even with their eyes closed, especially when trying to sleep. The phenomenon is harmless in the short term but raises concerns about cumulative exposure on long missions. Scientists continue to study the effects of cosmic rays on the visual system and brain. These strange, uninvited light shows are one of the more mysterious personal experiences of space travel. Bones become fragile enough to break on Mars return. The bone loss astronauts experience in microgravity has serious implications for missions to Mars. A round trip to the Red Planet could take 2 to 3 years, during which astronauts would lose substantial bone density despite exercise countermeasures. By the time they arrive on Mars, their skeletons might be weakened enough that a simple fall could cause fractures. Martian gravity is only about 1/3 of Earth's, offering some relief but not enough to fully reverse the decline. Returning astronauts face the additional challenge of readapting to Earth's stronger gravity after years away. Without significant advances in bone preservation techniques, interplanetary travelers could return as medical invalids. Researchers are exploring drugs that slow bone resorption and mechanical devices that stimulate bone growth. Protecting the skeleton is one of the most critical medical challenges for long-duration space exploration. Every tool must be tethered during spacewalks. In the weightless environment outside a spacecraft, any object that slips from an astronaut's grasp will drift away forever. A dropped wrench does not fall to the ground, it floats off into orbit, potentially becoming a hazard to other spacecraft. To prevent this, every tool used during a spacewalk is attached to the astronaut's suit or to the worksite with tethers and lanyards. Crew members spend considerable time before each spacewalk organizing their tool caddy and confirming that every item is secured. Despite these precautions, accidents happen, and some tools have been lost to the void over the years. Lost items become tracked debris, monitored by ground controllers to avoid collisions. The discipline of keeping everything tethered is drilled into astronauts during underwater training. Managing tools in space requires a level of patience and attention that would be unusual on Earth. Toilets in space use air instead of water. Gravity is essential for conventional plumbing, which is why spacecraft toilets operate on an entirely different principle. Instead of water flushing waste into a bowl, space toilets use airflow to direct waste into sealed containers. Astronauts must position themselves carefully over specially shaped openings, while a fan creates suction to capture urine and solid waste. Urine is collected and recycled into drinking water through advanced filtration systems. Solid waste is dried, compacted, and stored for eventual disposal or return to Earth for study. Using the toilet requires training, and new crew members practice with a camera-equipped training toilet on the ground. Despite the unusual process, modern space toilets are reasonably comfortable and hygienic. The engineering behind these systems is surprisingly complex, a testament to how every aspect of life must be reimagined without gravity. Solar storms can be deadly for astronauts. The Sun periodically erupts with coronal mass ejections and solar particle events that send waves of high-energy radiation rushing through the solar system. On Earth, the magnetosphere and atmosphere shield us from the worst effects, but astronauts in space have far less protection. A powerful solar storm could deliver a lethal dose of radiation to unshielded crew members within hours. Space agencies monitor solar activity closely and have plans to shelter astronauts in the most heavily shielded areas of the spacecraft during events. Future lunar or Mars habitats may include storm shelters surrounded by water tanks or regolith for added protection. The unpredictability of solar storms adds uncertainty to mission planning, especially for crews far from Earth who cannot quickly return. Developing better forecasting tools and shielding technologies is an ongoing priority for deep space exploration. You could run faster on the Moon than walk. Walking on the Moon is surprisingly awkward due to the combination of lower gravity and bulky spacesuits. With only 1/6 of Earth's gravity, each step sends astronauts bounding higher than intended, making it difficult to control forward motion. Apollo astronauts discovered that a loping run was often more efficient than a careful walk. By leaning forward and bounding in long, low arcs, they could cover ground more quickly while maintaining better balance. The iconic footage of astronauts hopping across the lunar surface was not just playful, it was a practical adaptation to the environment. Future lunar explorers will benefit from improved suits that offer greater flexibility and mobility. Training for lunar surface work includes learning these movement techniques on Earth using suspended harness systems. Moving on another world requires learning to move in an entirely new way. Spacecraft have different atmospheres than Earth. The air inside a spacecraft is carefully engineered to keep astronauts healthy, while minimizing weight and complexity. Many early spacecraft and the current Russian spacecraft use a nitrogen-oxygen mix similar to Earth's atmosphere at near sea level pressure. American spacesuits, however, operate at lower pressure with pure oxygen to reduce bulk and improve flexibility. Before spacewalks, astronauts must pre-breathe pure oxygen for hours to purge nitrogen from their blood and prevent decompression sickness. The International Space Station maintains a comfortable atmosphere but includes equipment to scrub carbon dioxide and add oxygen as needed. Fire safety is a major concern in oxygen-rich environments, leading to strict controls on flammable materials. Managing the atmosphere involves monitoring humidity, removing trace contaminants, and regulating temperature. Every breath an astronaut takes depends on technology working flawlessly around the clock. The International Space Station is always falling towards Earth. Orbit is essentially a continuous state of freefall. The International Space Station does not float motionless in space. It is constantly falling toward Earth, while simultaneously moving forward fast enough that it keeps missing the planet. This balance between gravitational pull and forward velocity creates the sensation of weightlessness for everyone aboard. If the station suddenly stopped moving forward, it would plummet back to Earth and burn up in the atmosphere. Astronauts inside experience microgravity, not because gravity is absent, but because they are falling along with the station at the same rate. This understanding of orbit dates back to Newton, who imagined a cannonball fired fast enough to fall around the Earth endlessly. The physics of orbital mechanics might seem counterintuitive, but they are the foundation of all modern satellite and space station operations. The Milky Way might have a specific smell. Scientists studying the chemistry of interstellar space have discovered compounds that, on Earth, are associated with distinct odors. One such molecule, ethyl formate, is found in the dust clouds of our galaxy and is responsible for the smell of rum and raspberries. Another common compound, hydrogen sulfide, would produce a rotten egg odor. Of course, smelling interstellar space directly is impossible because humans cannot survive in a vacuum. The residue of space that clings to spacesuits and equipment hints at a burnt, metallic scent, likely from polycyclic aromatic hydrocarbons. If one could somehow sample the Milky Way's gases in a safe environment, the result might be a strange cocktail of fruit, smoke and sulfur. These discoveries add a poetic dimension to astrophysics, suggesting that even the cosmos has its own sensory signature. Astronauts age slower in space due to time dilation. Relativity tells us that time flows differently depending on speed and gravity. Astronauts orbiting Earth are moving at tremendous velocities compared to people on the surface, causing their clocks to tick very slightly slower. Over the course of a year-long mission, an astronaut might age a tiny fraction of a second, less than an identical twin who stayed on the ground. The effect is measurable but imperceptible in daily life. However, if spacecraft could approach the speed of light, time dilation would become dramatic. A traveler on a relativistic journey might return to find that decades or centuries had passed on Earth, while only years went by for them. This fascinating consequence of physics has inspired countless science fiction stories and raises profound questions about the future of interstellar travel. Space truly bends the fabric of time itself. Returning astronauts must relearn how to walk. Months of living in microgravity profoundly affect the body's balance and coordination systems. When astronauts return to Earth, they often struggle to stand, walk, or even sit upright without assistance. The inner ear, which senses orientation and motion, must recalibrate to gravity after months of receiving no gravitational input. Muscles that have weakened during spaceflight must relearn how to support the body against the pull of Earth. Many astronauts describe feeling extremely heavy, as if an invisible weight is pressing down on them. Medical teams monitor returning crew members closely and provide support as they regain their land legs. The readjustment period can last days or weeks, depending on the length of the mission. Even the simple act of putting one foot in front of the other becomes a triumph after months floating among the stars. Mars has dust storms that cover the entire planet. Martian weather can produce dust storms of staggering proportions, sometimes growing large enough to envelop the whole planet for months. These global dust events are driven by temperature differences between the sun-warmed equator and colder polar regions, which generate fierce winds. Fine particles are lifted high into the thin atmosphere and spread across thousands of kilometers. During a major dust storm, the sky darkens to an ominous orange-brown, and solar-powered equipment can lose significant energy. The Mars rovers have experienced these storms firsthand, with one such event contributing to the loss of the Opportunity rover. Future human missions will need to plan for extended periods when solar power is unreliable and outdoor activities are limited by poor visibility. Dust accumulation on surfaces and equipment is also a long-term maintenance concern for any Martian settlement. Space causes medical conditions that have no Earth equivalent. Living in microgravity exposes the human body to stresses it never evolved to handle. Some conditions that develop in space have no true counterpart in terrestrial medicine. Spaceflight-associated neuroocular syndrome involves changes to the eyes and brain structure that can cause permanent vision problems. Fluid shifting and bone loss occur at rates unseen in healthy people on Earth. Immune system dysfunction in space does not match any known disease pattern. These unique conditions force researchers to develop new treatments and countermeasures specifically for space travelers. Each long-duration mission provides valuable data on how the body adapts and sometimes struggles. The field of space medicine continues to grow as humanity prepares for journeys beyond the familiar confines of low Earth orbit. Micrometeorites strike spacecraft every day. Space may look empty, but it is filled with countless tiny particles left over from comets, asteroids, and past collisions. These micrometeorites travel at speeds of tens of kilometers per second and can strike spacecraft at any moment. Most are smaller than grains of sand, but even tiny impacts at such velocities can pit surfaces, damage sensors, and scratch windows. The International Space Station has exterior shielding designed to absorb the energy of small impacts and protect vital systems from penetration. Over time, accumulated impacts create a cratered, worn appearance on exposed surfaces that tells the story of years in the harsh environment. Larger debris is tracked by ground controllers who adjust the station's orbit when necessary to avoid collisions. Micrometeorite impacts are a constant, invisible hazard that engineers must account for in every mission design. Living in space means accepting that the environment is perpetually trying to scratch, pierce, and erode your protective shell. Astronauts can see entire weather systems from orbit. From the vantage point of the International Space Station, astronauts witness Earth's atmosphere in ways impossible from the ground. Hurricanes appear as vast, swirling white pinwheels hundreds of kilometers across, their structure revealed in stunning clarity. Thunderstorm cells flash with lightning that illuminates entire cloud structures in brief moments of brilliance. The jet stream and trade winds trace visible patterns in the clouds below. Watching a weather system develop and migrate across continents in real time gives astronauts a visceral sense of the planet as a living, breathing entity. They have photographed volcanic eruptions, forest fires, and dust storms reaching across oceans. These images contribute to scientific understanding and help communicate the beauty and fragility of Earth. Many astronauts describe the overview effect, a profound shift in perspective where political borders seem meaningless compared to the unity of the biosphere. Seeing Earth from above changes how one thinks about home forever. Astronauts receive higher radiation doses than nuclear workers. Space radiation exposure significantly exceeds the occupational limits set for workers in nuclear industries on Earth. Astronauts on the International Space Station receive roughly 1 millisievert of radiation per day, equivalent to about 3 chest X-rays. Over a 6-month mission, their total dose can approach the annual limit for nuclear plant employees. Beyond low Earth orbit, where the planet's magnetic field offers less protection, radiation levels increase dramatically. Mars-bound astronauts would accumulate even higher doses during the months of interplanetary transit. This increased exposure raises the lifetime risk of cancer and other health problems. Space agencies carefully track each astronaut's cumulative radiation and limit the number of missions accordingly. Developing better shielding and possibly new medical countermeasures is a priority as humanity ventures further from the safety of Earth. Sound cannot travel through the vacuum of space. Sound waves require a medium like air, water, or solid material to travel. In the vacuum of space, there are virtually no molecules to carry these vibrations, rendering the environment perfectly silent. Explosions, engine burns, and collisions that would be deafening on Earth occur in complete silence outside a spacecraft. This is why science fiction movies that depict roaring rocket engines and booming space battles are physically inaccurate, though they make for exciting entertainment. Astronauts communicate through radio waves, which are electromagnetic and do not require a medium to propagate. Inside a pressurized spacecraft, normal sounds exist because air is present to vibrate. The stark contrast between the noisy interior and the silent void outside reminds us how fundamentally different the space environment is from everyday life on Earth. Silence in space can be both peaceful and profoundly unsettling. The first footprints on the Moon will last for millions of years. The lunar surface has no atmosphere, wind, or water to erode features the way Earth does. Footprints left by Apollo astronauts more than half a century ago remain exactly as they were, sharp and pristine. Rover tracks, boot prints, and equipment imprints stand frozen in time, slowly being modified only by micrometeorite bombardment over vast timescales. Scientists estimate these marks could persist for tens of millions of years before being significantly degraded. This makes the Moon a remarkable archive of human activity and a permanent monument to early space exploration. The knowledge that bootprints can outlast entire civilizations adds a humbling dimension to lunar missions. Future visitors will be able to walk among these historic sites and see the evidence of humanity's first steps beyond Earth. Every step an astronaut takes becomes a potential archaeological treasure for future generations to discover and study. Spacecraft can develop tiny holes during missions. In an emergency, anything that can block air from escaping becomes a life-saving tool. There have been documented incidents where astronauts discovered tiny leaks and used gloved thumbs or even tape to seal them until permanent repairs could be made. The small surface area of a pinhole means the pressure differential is manageable for brief periods. While this is not a recommended repair method, it buys precious time and prevents rapid depressurization while the crew prepares a proper patch. Spacecraft carry repair kits designed for patching minor punctures, often using specialized epoxies and metal plates. The famous Soyuz leak in 2018 was initially identified by covering potential breaches with tape before a permanent fix was applied. Quick thinking under pressure is a critical astronaut skill. The anecdote of plugging a hole with a finger captures the ingenuity sometimes required in space emergencies. Astronauts wear gold-coated visors to block sunlight. The sun in space is far more dangerous than it appears from Earth's surface because there is no atmosphere to filter its radiation. Spacesuit helmet visors are treated with a thin gold coating that reflects infrared radiation and reduces heat load. Gold is an excellent reflector of certain wavelengths and protects astronauts' eyes from intense brightness without distorting visible light too much. The visor also blocks harmful ultraviolet rays that could cause eye damage. This golden tint is one of the most visually distinctive features of modern spacesuits. The technology is borrowed from fighter pilot helmets, where similar coatings protect aviators at high altitudes. Without this protective layer, spacewalks facing the sun would risk serious injury. The gleaming golden helmet is more than just an iconic image. It is essential safety equipment. Bacteria behave differently in microgravity. Laboratory experiments aboard the Space Shuttle and the International Space Station have shown that some bacteria grow faster and become more dangerous in space. Studies on Salmonella found that microgravity increased virulence and resistance to environmental stresses. The low-shear fluid environment around cells mimics conditions inside certain parts of the human body, triggering genetic changes that enhance pathogenicity. This has implications for astronaut health, as an infection in space could progress more rapidly than on Earth. At the same time, the immune system is weakened by spaceflight, creating a troubling double threat. Researchers are working to understand these mechanisms and develop countermeasures. Space-based biology research could eventually lead to new antibiotics or therapies useful on Earth. Bacteria's behavior in orbit is a surprising lesson in how profoundly microgravity affects living organisms. Materials can be made stronger in zero gravity. Microgravity eliminates the convection and sedimentation caused by gravity on Earth, allowing scientists to study material processes in pure form. Metal alloys formed in space often have fewer defects and more uniform structures than those made on the ground. Crystal growth proceeds without the buoyancy-driven flows that disrupt formation on Earth, resulting in larger and more perfect specimens. Protein crystals grown in orbit have advanced drug development research by revealing molecular structures more clearly. Fiber optics manufactured in microgravity can achieve purity impossible under gravity's influence. The International Space Station serves as a unique laboratory for testing advanced materials and manufacturing techniques that could benefit industries on Earth. Industrial processes like semiconductor production may one day benefit from space-based facilities. Zero gravity is not just a novelty, it is a powerful tool for creating stronger, purer, and more advanced materials. It takes months to mentally prepare for a space mission. Physical fitness and technical expertise are only part of astronaut training. Psychological preparation is equally vital. Living in a confined space with a small crew for months requires exceptional emotional stability and interpersonal skills. Training includes isolation exercises, conflict resolution workshops, and simulations of high-stress scenarios that test mental resilience. Candidates are carefully screened for personality traits that predict resilience under pressure. Once in space, crew members have access to psychological support through private communication with therapists on Earth. Mental health is monitored just as closely as physical health, with mission control ready to intervene if necessary. Long-duration missions to the Moon and Mars will intensify these challenges due to communication delays and extreme isolation. Preparing the mind for space is as demanding and important as preparing the body. Astronauts must learn to cry without gravity. The human body can still produce tears in microgravity, and astronauts certainly experience emotions that might make them cry. Without gravity to pull them down, however, tears form a growing blob that clings to the eye and surrounding skin. The sensation is described as uncomfortable, with a liquid mass sticking to the face rather than streaming away. Eventually, the tearball becomes large enough to wobble or break free, floating off as a shimmering sphere. Astronauts have captured video of this strange phenomenon for educational outreach. The inability of tears to fall affects more than just crying. Any eye irritation allows liquid to accumulate rather than drain naturally. This seemingly mundane difference underscores how many everyday experiences change profoundly in space. Even sorrow and relief look different beyond the grip of Earth's gravity. The vacuum of space can boil blood instantly. The vacuum of space has essentially zero atmospheric pressure, and liquids boil at much lower temperatures under such conditions. Exposed to this environment without protection, the fluids in a human body would begin to vaporize. Saliva on the tongue would boil first, followed by moisture in the tissues and eyes. This gruesome scenario would not kill instantly, but would cause rapid incapacitation, unconsciousness within about 15 seconds, and death shortly after. Spacesuits and spacecraft maintain internal pressure precisely to prevent this fate from ever happening. The terrifying reality underscores why puncture and seal integrity are obsessive concerns for mission designers. Even a small failure can have catastrophic consequences in the unforgiving vacuum. Every spacewalk carries the implicit risk of this nightmarish possibility should something go wrong. Landing on Mars is like stopping a car on a frozen pond. Mars presents a landing challenge unlike any other body in the solar system. Its atmosphere is thick enough to generate dangerous heat during entry, but too thin to slow a spacecraft sufficiently with parachutes alone. Engineers must combine heat shields, parachutes, retro-rockets, and even sky crane systems to land safely. The infamous 7 minutes of terror describes the critical phase when a Mars lander descends, mostly autonomously, with no real-time control from Earth. Communication delays of up to 20 minutes mean ground controllers can only watch and hope. Just as a car sliding on ice cannot stop quickly despite applying brakes, a Mars lander struggles to shed velocity in the thin atmosphere. More than half of all Mars missions have failed, many during landing attempts. Each successful touchdown is a major engineering triumph, requiring innovations that push the boundaries of aerospace technology. There is no privacy in space. Living aboard the International Space Station means sharing every moment with crewmates in tight quarters. Private cabins are smaller than a phone booth, offering barely enough room to sleep in a secured sleeping bag. There are no doors that truly shut out the world, and sounds travel easily through the modules. Personal calls with family are scheduled and take place using headsets to minimize disturbance, but true solitude is rare. Even basic activities like changing clothes or using the restroom require creative scheduling to maintain dignity. Crew members quickly develop an unspoken etiquette about personal space and boundaries that allows everyone to coexist. Psychological training prepares astronauts for this constant togetherness, but it remains one of the hardest adjustments. The lack of privacy can strain relationships over long missions, making interpersonal skills essential for survival. The closest thing to a shower in space is a damp towel. Without gravity, water does not flow downward, making traditional showers impossible. Astronauts clean themselves using wet wipes, no-rinse shampoo, and damp towels. They squeeze small amounts of water onto their skin and rub it around, then wipe away the moisture before it floats off. Washing hair involves applying a foaming shampoo that does not need rinsing and toweling it dry. The entire process feels more like a sponge bath than a refreshing shower. Some astronauts describe it as functional, but far from satisfying. Water conservation is critical because every drop must be recycled from humidity, sweat, and even urine. Despite the limitations, staying clean is essential for morale and health. Astronauts adapt quickly but often cite long hot showers as one of the first pleasures they seek upon returning home. Astronauts do experiments while floating freely. Microgravity transforms the laboratory experience in ways impossible to replicate on Earth. Researchers float alongside their equipment, positioning themselves with gentle pushes and handholds. Test tubes, samples, and instruments must be secured to prevent them from drifting away mid-experiment. Astronauts become skilled at working with one hand while anchoring their bodies with the other. This unique environment allows studies on crystal growth, combustion, fluid dynamics, and biology that require the absence of gravitational influences. The process is slower and requires careful choreography, but the scientific value is immense. Floating freely while manipulating delicate apparatus adds a surreal dimension to routine research. Many astronauts describe the experience as both challenging and exhilarating. Science in orbit is a dance between human ingenuity and the peculiar physics of weightlessness. Spacecraft windows must be replaced due to micrometeoroid damage. The windows on spacecraft endure constant bombardment from tiny particles traveling at tremendous speeds. Over time, these impacts create pits, scratches, and weakened spots that compromise optical clarity and structural integrity. The International Space Station has multiple layers of glass with replaceable outer panes designed to absorb most damage. Astronauts periodically inspect windows and document new marks, and some panes have been replaced during resupply missions. A single well-placed strike could, in theory, create a catastrophic breach, though shielding minimizes this risk. The cupola, the station's favorite observation post, receives special attention because of its importance to crew morale and Earth observation photography. Even with precautions, the slow degradation of windows is inevitable. Living in space means accepting that your view of the cosmos comes through glass, under constant assault. Mars has seasons that are twice as long as Earth's. Mars orbits the Sun in about 687 Earth days, making its year nearly twice as long as ours. Because the planet has a tilted axis similar to Earth's, it experiences distinct seasons: spring, summer, autumn, and winter. Each Martian season lasts roughly twice as long as its Earth counterpart, meaning a Martian summer stretches for about 6 months. The planet's elliptical orbit causes southern summers to be shorter and warmer, while northern summers are longer and cooler. Dust storms often erupt during southern summer, when the planet is closest to the Sun and heating is most intense. future colonists would need to adapt to extended growing seasons and prolonged winters. Understanding Martian seasons is crucial for planning missions, agriculture, and energy production. The Red Planet's calendar would reshape the rhythm of daily life for anyone living there. You can see entire continents pass beneath you every 90 minutes. The International Space Station orbits Earth roughly every 90 minutes, completing about 16 orbits per day. From this vantage point, astronauts watch continents, oceans, and weather systems drift past at a leisurely yet relentless pace. In a single orbit, the crew might observe sunrise over Africa, fly above the Pacific, and witness night falling over Asia. The shifting view provides a constant reminder of Earth's beauty and fragility. Photographs taken from orbit capture hurricanes, desert dust storms, city lights at night, and the thin blue line of atmosphere. Many astronauts describe gazing out the window as one of the most profound experiences of spaceflight. The rapid succession of daylight and darkness can be disorienting at first, but becomes a unique rhythm of life in space. Watching the world spin beneath you never loses its magic. Spacecraft can charge themselves with electricity just by moving. As a spacecraft travels through the plasma environment of space, it can accumulate static charge, much like shuffling across a carpet. This phenomenon, called spacecraft charging, occurs when electrons and ions bombard the surface at different rates. High-energy particles from the Sun and trapped radiation in planetary magnetic fields contribute to the effect. If parts of the spacecraft become charged differently, arcing can occur, potentially damaging electronics or triggering false sensor readings. Engineers designed spacecraft with conductive coatings and grounding systems to distribute charge evenly and prevent dangerous buildups. Understanding spacecraft charging is essential for missions passing through Earth's radiation belts or exploring outer planets. The phenomenon is invisible, but can have severe consequences if not managed. Electricity generated passively by motion through space is yet another hazard engineers must anticipate and mitigate. Spacesuits weigh more than an astronaut on Earth. A fully equipped NASA Extravehicular Mobility Unit, the white suit used for spacewalks, weighs approximately 127 kilograms on Earth. This mass includes life support systems, layers of protective materials, communication equipment, and a rigid torso shell. On Earth, moving in such a suit would be nearly impossible due to the crushing weight. In microgravity, however, the suit floats effortlessly, and astronauts focus on managing its bulk and stiffness rather than its weight. Pressurized gloves remain one of the biggest mobility challenges, limiting dexterity during delicate tasks. The suit is essentially a human-shaped spacecraft, providing oxygen, temperature control, and radiation protection. Donning and doffing the suit takes considerable time and assistance. Despite its cumbersome nature, the spacesuit is a marvel of engineering that keeps humans alive in the deadliest environment imaginable. There is a growing debate about who owns space. The Outer Space Treaty of 1967 established that no nation may claim sovereignty over celestial bodies, but commercial interests are testing these principles. Companies planning to mine asteroids or extract lunar water argue that resource ownership is different from territorial claims. Some countries have passed laws allowing their citizens to own materials extracted from space. Others view such legislation as a violation of international agreements. The Moon, Mars, and asteroids may contain trillions of dollars in valuable minerals, making the stakes extraordinarily high. Legal scholars, diplomats, and entrepreneurs are actively debating how property rights should work beyond Earth. Without clear rules, conflicts could arise as more actors enter space. The ownership question will shape humanity's future in the cosmos for generations to come. Even breathing in space is a technology problem. Humans require a steady supply of oxygen and a way to remove exhaled carbon dioxide, neither of which space provides naturally. Aboard the International Space Station, electrolysis splits water molecules to generate oxygen, while chemical scrubbers absorb carbon dioxide from the air. Backup canisters of compressed oxygen are available for emergencies. The entire life support system must operate continuously without failure, since even a few hours without proper air could endanger the crew. Early spacecraft relied on stored oxygen tanks, but for long-duration missions, recycling is essential. The technology to maintain breathable air has improved enormously since the first human spaceflights, but remains a critical engineering challenge. Every breath an astronaut takes is a testament to decades of innovation. Keeping humans alive in space starts with solving the fundamental problem of generating and managing air. Robots may build the first homes on Mars. Sending humans to Mars is extraordinarily expensive and dangerous, so scientists propose deploying robots first to prepare habitats. Autonomous machines could excavate underground shelters, 3D print structures from Martian soil, and set up life support systems before any crew arrives. NASA and private companies are developing rovers and robotic arms capable of construction tasks in harsh environments. Using local materials, known as in situ resource utilization, dramatically reduces the mass that must be launched from Earth. Robots do not need food, water, or oxygen, making them ideal pioneers for the most inhospitable frontier. Once basic infrastructure is in place, humans would arrive to a partially ready home, rather than starting from scratch. This phased approach minimizes risk and maximizes efficiency. The first colonists on Mars may owe their survival to machines that worked silently for years before their arrival. Water behaves like living jelly in space. Without gravity to pull it downward, water in microgravity forms wobbly spheres that quiver and oscillate at the slightest touch. Surface tension dominates, shaping liquids into perfect globes that drift through the cabin. Astronauts can nudge a water ball and watch it wobble hypnotically, its surface undulating like a living organism. Drinking requires squeezing pouches directly into the mouth to prevent floating droplets from escaping. Spilled water is a nuisance because it clings to surfaces and electronics rather than pooling on the floor. Experiments with water in space have revealed surprising behaviors impossible to observe on Earth. Videos of floating water spheres have become popular educational content, illustrating fundamental physics in an engaging way. The simple act of interacting with water becomes a surreal experience when gravity is removed from the equation. Most astronauts bring a personal item to space. Space agencies allow astronauts to carry a small number of personal items, recognizing the psychological importance of mementos. These items might include family photos, wedding rings, religious symbols, or small keepsakes from loved ones. Some astronauts have brought flags, musical instruments, or tokens from organizations they support. The mass and volume are strictly limited, so each item must be carefully chosen. Having a piece of home in orbit provides comfort during long missions, far from family and familiar surroundings. Personal items often make appearances in photographs and videos shared with the public. After returning to Earth, these objects become priceless souvenirs of an extraordinary journey. The tradition highlights the human side of space exploration, reminding us that astronauts are not just professionals but people with deep personal connections. You can watch a sunrise every 90 minutes in orbit. The International Space Station completes one orbit of Earth approximately every 90 minutes, resulting in 16 sunrises and sunsets each day. Each sunrise is a rapid explosion of color as the sun crests the curved horizon, turning the atmosphere from black to vivid orange and blue in seconds. The transition from day to night happens swiftly, plunging the station into darkness before another dawn arrives less than an hour later. Astronauts never tire of watching this spectacle through the cupola windows. The rapid cycling of light and dark can disrupt circadian rhythms, so crew members use scheduled lighting and eye masks to maintain a healthy sleep schedule. Watching the sunrise from orbit is described as both beautiful and disorienting. The experience redefines concepts of day and night for anyone who lives it. 16 sunrises a day is one of the many surreal realities of life in space. Every mission leaves behind a trail of forgotten artifacts. Space exploration has scattered debris across the solar system, from spent rocket stages circling Earth to rovers resting silently on Mars. The Moon is dotted with landers, flags, footprints, and even bags of human waste from Apollo missions. Defunct satellites and lost equipment form an ever-growing cloud of orbital debris. Some artifacts, like the Voyager probes, carry messages intended for any intelligence that might find them millions of years from now. These objects are unintentional time capsules, preserving a snapshot of human technology and ambition. Future archaeologists, whether human or otherwise, could study them to understand early spaceflight. The trail of forgotten items is both a legacy and a liability, as debris threatens active missions. Every journey to space adds to this silent collection drifting through the void. A spaceship must carry fire, air, food, water, and gravity. Designing a spacecraft for human habitation means recreating the essentials of Earth in a sealed capsule hurtling through the void. Life support systems generate oxygen, scrub carbon dioxide, and maintain comfortable temperature and humidity. Water is recycled from humidity, sweat, and urine, then purified for drinking and hygiene. Food is carefully packaged to remain nutritious and palatable for months or years. Fire in the controlled sense powers cooking and sterilization when needed, though open flames are dangerous in enclosed spaces. Artificial gravity remains elusive, but rotating habitats or exercise regimens attempt to mitigate its absence. Every system must be redundant and repairable, because failure means death. The spaceship becomes a miniature, self-contained world, carrying everything needed to sustain life. Engineering such a vessel is one of humanity's greatest technical achievements. You can hear the space station creak and moan. The International Space Station is not silent inside. Its structure shifts and groans as temperatures change with each orbit. When the station passes into sunlight, metal expands, and when it enters shadow, the metal contracts. These thermal cycles cause audible creaking and popping sounds that travel through the hull. New crew members are often startled by the noise until they learn its source. Fans, pumps, and machinery add a constant background hum that some astronauts find soothing, like white noise. The combination of mechanical sounds and structural creaks creates a unique acoustic environment. Living on the station means accepting that your home is a living machine making its own symphony. The noises become familiar, a reminder that the station is a dynamic structure surviving in an extreme environment. Spacesuits must be pressurized like balloons. A spacesuit creates a pressurized bubble of air around the astronaut to prevent bodily fluids from boiling in the vacuum. Inside the suit, pressure is maintained at about 1/3 of sea level atmospheric pressure using pure oxygen. This lower pressure allows the suit to be more flexible while still protecting the wearer. The pressurized environment stiffens joints and gloves, making every movement require effort. Astronauts train extensively to work efficiently within these constraints. Leaks in the suit are life-threatening emergencies that must be addressed immediately. Engineers constantly seek new materials and designs to improve flexibility without sacrificing safety. The comparison to a balloon is apt. Without pressure, the suit and its occupant cannot survive. Every spacewalk is a test of how well humans can function inside an inflated cocoon of life-sustaining fabric. Venus is a deadlier destination than Mars. While Mars is often discussed as the next frontier, Venus presents conditions that would destroy any current spacecraft and crew. Surface temperatures on Venus exceed 450 degrees Celsius, hot enough to melt lead. Atmospheric pressure is roughly 90 times that of Earth, equivalent to being nearly a kilometer underwater. Clouds of sulfuric acid shroud the planet, and the thick atmosphere traps heat in a runaway greenhouse effect. Any lander would be crushed and corroded within hours. Proposals exist for floating habitats in the upper atmosphere, where conditions are milder, but landing on the surface remains impractical. Mars, by contrast, offers thin but manageable atmosphere, survivable temperatures with insulation, and accessible water ice. Venus reminds us that not all worlds are hospitable, even among our nearest neighbors. The hellish environment makes Mars look almost welcoming by comparison. Space farming could make us a multi-planet species. Growing food beyond Earth is essential for any long-duration mission or permanent settlement. Experiments on the International Space Station have successfully cultivated lettuce, radishes, and other crops in controlled chambers. Plants provide not only nutrition but also oxygen and psychological benefits for isolated crews. Future Mars colonies would rely on greenhouses shielded from radiation and supplied with recycled water and nutrients. Developing crops that thrive in low gravity, limited light, and confined spaces is an active area of research. Self-sustaining agriculture reduces dependence on resupply missions from Earth. Once a colony can feed itself, the dream of becoming a multi-planet species moves from science fiction to reality. Space farming is the foundation upon which humanity could build permanent outposts across the solar system and beyond. Future space habitats might spin to create gravity. Artificial gravity could solve many of the health problems caused by microgravity on long-duration missions. A rotating habitat generates centripetal acceleration that mimics gravitational pull, keeping occupants pressed against the outer wall. Science fiction has long envisioned spinning wheel-shaped stations, and engineers are studying how to build them practically. The rotation rate must be carefully chosen to avoid motion sickness while providing meaningful gravity. Such habitats would allow normal walking, running, and sleeping without restraints. Bones and muscles would experience loads similar to Earth, preventing the deterioration seen on current space stations. Constructing spinning habitats in orbit is technically challenging and expensive, but the benefits for crew health could be decisive for missions lasting years. Spinning stations may become the standard design for humanity's expansion into deep space. Space travelers must learn to live with constant danger. Every moment in space carries risks that simply do not exist on Earth. Radiation bombardment, micrometeorite impacts, and equipment failures are ever-present threats. A small leak, a malfunctioning life support system, or a solar flare could turn routine operations into life-or-death emergencies. Astronauts train endlessly for these scenarios, building skills and reflexes that might save their lives. Accepting this constant danger requires psychological resilience and trust in one's crew and equipment. The awareness of risk never fully fades, becoming a background hum in the mind. Space agencies manage danger through redundancy, rigorous procedures, and continuous monitoring. Living with the knowledge that safety is never guaranteed is part of what makes astronauts extraordinary. The frontier of space rewards only those who can embrace peril as a companion. Human bodies may evolve differently on other planets. If humans settle on Mars or other worlds for generations, natural selection and adaptation could alter our species. Lower gravity would reduce the need for dense bones and strong muscles, potentially leading to lighter, taller body types. Higher radiation environments might favor genetic mutations that provide some protection. Isolation from Earth's population could accelerate divergence, creating distinct human subspecies over millennia. These changes are speculative, but grounded in evolutionary biology. Future Martians might eventually be unable to live comfortably on Earth, completing a biological split. The ethical and social implications of such divergence are profound and largely unexplored. Space colonization is not just a technological challenge, but a potential turning point in human evolution. Our descendants in the stars may look and function differently than we do today. Dust on the moon smells like gunpowder. Apollo astronauts reported that lunar dust clinging to their suits had a distinct odor once inside the cabin. The smell was often compared to burnt gunpowder or spent fireworks. This may result from the oxidation of iron-rich particles when exposed to oxygen and moisture in the lunar module. On the airless moon, these particles never react, but in a breathable atmosphere they become chemically active. The tiny, sharp-edged grains are also hazardous to lungs and equipment, presenting challenges for long-term habitation. Managing dust will be a critical concern for future lunar bases. Filters, airlocks, and protective suits must prevent contamination of living spaces. The strange smell of the moon is a sensory detail that makes space exploration feel unexpectedly personal. Even alien worlds leave impressions on our most basic senses. A dead satellite can drift for centuries. When a satellite runs out of fuel or suffers a critical failure, it does not fall immediately. Depending on its altitude, it may continue orbiting Earth for decades or even centuries. In low Earth orbit, atmospheric drag gradually pulls objects down, but higher orbits have negligible drag. Geostationary satellites, for example, can remain in place almost indefinitely unless moved to a graveyard orbit. These defunct objects become debris hazards, posing collision risks to active spacecraft. Tracking dead satellites is essential for space traffic management. Some proposals call for active debris removal missions to capture and deorbit large defunct satellites. Without intervention, the population of dead spacecraft will only grow as more nations and companies access orbit. Each silent hulk is a monument to missions past, and a challenge for missions yet to come. Space mining could power entire civilizations. Asteroids and moons contain vast quantities of metals, water, and rare elements that could fuel humanity's future. A single metallic asteroid could hold more platinum group metals than have ever been mined on Earth. Water extracted from icy bodies could be split into hydrogen and oxygen for rocket fuel, enabling deep space exploration. Mining operations in space would reduce the environmental impact of resource extraction on our home planet. Companies and governments are already investing in prospecting missions to identify promising targets. The legal and logistical challenges are enormous, but the potential rewards are staggering. space mining could become the foundation of an interplanetary economy, driving innovation and expansion. Resources floating in the void might one day sustain billions of people both on and off Earth. Spacecraft must carry their own magnetic fields. Earth's magnetic field shields us from much of the Sun's harmful radiation, but spacecraft venturing beyond low Earth orbit lose this protection. Proposals exist for generating artificial magnetic fields around spacecraft or habitats to deflect charged particles. Superconducting magnets or plasma shields could create a protective bubble similar to Earth's magnetosphere. Such technology is still experimental, but it may be essential for crewed missions to Mars and beyond. Without shielding, astronauts face elevated cancer risks and possible neurological damage. Active magnetic protection would require significant power and engineering innovation. Passive shielding with water or materials is another approach, but adds mass. The challenge of carrying one's own magnetic shield underscores how hostile the space environment truly is. Solving this problem is a key step towards sustainable human presence off Earth. The first baby born on Mars will never be fully Earthling. A child conceived and born on Mars would grow up in an environment entirely unlike our home world. Lower gravity, higher radiation, and a completely artificial atmosphere would shape their development in unknown ways. Their bones and muscles might never adapt to Earth's gravity, making a visit to the ancestral planet physically dangerous. Culturally and psychologically, they would identify with Mars as home rather than Earth. This individual would represent a new chapter in human history, the first true Martian. Legal questions about citizenship and rights would need answers that no existing framework provides. The birth would mark the definitive moment when humanity becomes a multi-planet species. What begins as a single child would eventually become a new branch of the human family tree. The first Martian is a symbol of possibilities both thrilling and sobering. Astronauts see invisible light with special cameras. The human eye perceives only a narrow slice of the electromagnetic spectrum, but spacecraft carry instruments that see far beyond. Infrared cameras reveal heat signatures, showing temperature variations on Earth's surface and in space. Ultraviolet sensors detect emissions from stars and hot gases that visible light cannot capture. X-ray and gamma-ray telescopes observe the most energetic phenomena in the universe. Astronauts use these tools to conduct research impossible from the ground, where the atmosphere blocks many wavelengths. Imaging in invisible light has led to discoveries about black holes, supernovae, and cosmic structure. The ability to see beyond human senses expands our understanding of the cosmos. Each new wavelength opens a window onto a different aspect of reality. In space, astronauts become the operators of eyes far more powerful than any evolution provided. In space, you can only tell time by Earth. Without the natural cues of sunrise and sunset, astronauts rely on clocks synchronized to a standard Earth time zone. The International Space Station operates on coordinated universal time, providing a consistent schedule for the international crew. Mission events, sleep periods, and communication windows are all planned according to Earth clocks. This dependence on terrestrial time is more than practical. It is psychological, maintaining a link to home. Future missions to Mars will face the challenge of a day nearly 40 minutes longer than Earth's, gradually shifting out of sync. Over months, Martian colonists would live on a completely different rhythm from friends and family back home. Timekeeping becomes a subtle but constant reminder of the distance traveled. Until new conventions are established, the clock on the wall will always point back to Earth. You can run around an entire asteroid in minutes. Many asteroids are so small that their surface gravity is negligible, allowing a person to travel at walking pace yet cover vast distances. On a body only a few hundred meters across, a single jump could send you sailing around the entire circumference. The escape velocity of some asteroids is slower than a jog, meaning an enthusiastic sprint could launch you into orbit or off into space entirely. This surreal environment presents both opportunities and challenges for future miners and explorers. Tethers and anchoring systems would be essential to prevent crew members from drifting away. Navigating such a landscape would feel more like controlled floating than walking. The physics of tiny worlds defy everyday intuition, turning simple locomotion into an alien experience. Running around an asteroid is a reminder of how diverse the gravitational environments of our solar system truly are. Future Mars settlers will need new calendars. A Martian day, called a sol, is approximately 24 hours and 39 minutes long, close to Earth's but not quite the same. Over weeks and months, this difference accumulates, shifting Martian schedules out of alignment with Earth time. A Martian year lasts 687 Earth days, meaning seasons and anniversaries would follow a different rhythm. Colonists would likely develop a new calendar system suited to their world, perhaps with different month lengths and holidays. Coordinating with Earth for communication and supply missions would require constant conversion between the two timekeeping systems. The psychological impact of a fundamentally different calendar is hard to predict, but could foster a distinct Martian identity. New traditions and rituals would emerge to mark the passage of time on the red planet. The calendar is a small detail that underscores the profound transformation of becoming a two-planet species. Every space mission must carry its own shield against the sun. Solar radiation is far more intense in space than on Earth's surface, where the atmosphere and magnetic field provide natural protection. Spacecraft and habitats must incorporate shielding materials to reduce radiation exposure for both crew and sensitive electronics. Some missions use water-filled walls, polyethylene, or metals to absorb or deflect incoming particles. Solar flares can dramatically increase radiation levels on short notice, requiring sheltered safe rooms for astronauts. Deep space missions beyond Earth's magnetic influence face even greater challenges. Designing effective shielding is a balance between protection and mass, since heavier craft cost more to launch. Active monitoring of solar activity helps crews anticipate dangerous events. Carrying one's own shield against the sun is a non-negotiable requirement for survival beyond our protective atmosphere. We have simulated Mars on Earth to prepare for the real thing. Scientists and space agencies have built analog habitats in remote locations to test equipment and study human behavior under Mars-like conditions. Sites in the deserts of Utah, the volcanic slopes of Hawaii, and the polar regions of Canada and Antarctica serve as stand-ins for the red planet. Crews live in isolated modules for weeks or months, following communication delays and resource constraints similar to a real mission. These simulations reveal technical problems and interpersonal challenges before they become life-threatening in space. Psychological research tracks morale, conflict resolution, and cognitive performance under stress. Engineering teams use the data to improve habitat designs, life support systems, and operational procedures. Simulated missions are dress rehearsals for the ultimate journey. Every lesson learned on Earth reduces risk for the pioneers who will actually set foot on Mars. Space debris could trap humanity on Earth. The Kessler syndrome describes a scenario where cascading collisions between orbital debris create an ever denser cloud of fragments. Each collision generates more debris, which causes more collisions, eventually rendering certain orbits unusable. Critical satellites for communication, navigation, and weather forecasting would be destroyed or become too risky to operate. Launching new spacecraft through the debris field could become prohibitively dangerous, effectively trapping humanity on the planet. This nightmare scenario is not inevitable, but the growing population of defunct satellites and rocket stages makes it more plausible each year. International cooperation on debris removal and responsible satellite disposal is essential. Preventing the Kessler syndrome is one of the most important long-term challenges for spacefaring nations. Failure to address debris could end the space age before interplanetary exploration truly begins. Living on the Moon will require underground cities. The lunar surface is bombarded by cosmic rays, solar radiation, and micrometeorites that make open habitation extremely dangerous. Building underground or covering structures with regolith would provide shielding from these hazards. Lava tubes, natural tunnels created by ancient volcanic activity, could offer ready-made shelters large enough for entire settlements. Temperature underground is far more stable than on the surface, where swings between scorching heat and deep cold occur every 2 weeks. Excavation and construction in 1/6 gravity present unique engineering challenges that are only beginning to be explored. Underground habitats would need artificial lighting, ventilation, and careful structural support. Life in a lunar city might feel more like living in a cave than on another world. The Moon's hostile surface pushes colonists to seek refuge beneath the gray dust. Every space traveler has to be ready to fix the ship. Unlike a commercial airline passenger, an astronaut cannot simply wait for ground support when something breaks. Spacecraft carry tools and spare parts for repairs that must be performed by the crew, sometimes in emergencies. Training covers everything from patching leaks to replacing failed circuit boards and restoring life support functions. Astronauts study systems intensively so they can diagnose and fix problems under pressure. On missions far from Earth, communication delays make remote troubleshooting impractical. Self-reliance is a core survival skill when help is hours or days away. The ability to improvise solutions with limited resources has saved lives throughout spaceflight history. Every crew member must be part engineer, part mechanic, and part problem solver. In space, knowing how to fix the ship is as important as knowing how to fly it. A single bolt can scratch a spacesuit. Spacesuits are surprisingly vulnerable despite their advanced construction. The outer layers are designed to resist abrasion and puncture, but a sharp edge or protruding bolt can still cause damage. Even minor scratches can weaken the suit's protective fabric and create potential failure points. Astronauts are trained to move carefully and be aware of their surroundings at all times during spacewalks. Gloves are especially susceptible because they must be thin enough for dexterity, yet they handle tools and grip surfaces constantly. Regular inspections are conducted before and after every extravehicular activity. A small tear under vacuum conditions could escalate into a life-threatening emergency. The meticulous care taken to avoid damage highlights how delicate the barrier between astronaut and void truly is. Every bolt, bracket, and handle aboard the station must be designed with suit safety in mind. The first spaceship to leave the solar system is still sending messages. Voyager 1, launched in 1977, crossed into interstellar space in 2012 and continues to transmit data back to Earth. Its faint signals take more than 22 hours to travel the billions of kilometers separating the probe from home. Instruments still operating measure cosmic rays, magnetic fields, and plasma in the space between stars. The spacecraft carries a golden record containing sounds and images of Earth, intended for any intelligence that might someday find it. Voyager's longevity far exceeded its original mission and stands as a testament to engineering excellence. Power from its radioactive generators will eventually fade, silencing the probe sometime in the next decade. Until then, Voyager remains humanity's most distant ambassador, sailing through the void and occasionally whispering back. Its journey symbolizes the boundless curiosity that drives space exploration. A Mars colony must be a closed ecosystem. Resupply missions from Earth would take months and cost billions, making a self-sustaining colony essential for long-term viability. A closed ecosystem recycles air, water, and nutrients in continuous loops, without relying on external inputs. Plants convert carbon dioxide into oxygen and provide food, while waste products are composted or processed for reuse. Water is extracted from humidity, urine, and other sources, then purified and recirculated. Achieving true closure is immensely difficult. Even small leaks or inefficiencies accumulate over time. Earth's biosphere manages these cycles naturally, but a Martian habitat must engineer them from scratch. Research facilities like Biosphere 2 have tested closed systems on Earth with mixed results. Success on Mars would mean humanity could survive indefinitely far from our home world. The closed ecosystem is both a technical goal and a philosophical milestone. Spacecraft doors must seal perfectly, or everyone dies. The boundary between a pressurized cabin and the vacuum of space is maintained by airtight seals on every hatch and docking port. Even a tiny gap can allow life-sustaining air to leak out, leading to depressurization and death. Seals are designed with multiple redundancies and are inspected regularly for wear, debris, or damage. During docking maneuvers, confirmation of a perfect seal is mandatory before any hatch is opened. Astronauts are trained to respond instantly if an alarm indicates a pressure drop, rushing to close and secure affected compartments. The engineering of spacecraft doors involves exotic materials and meticulous manufacturing tolerances. A single overlooked flaw could turn a routine procedure into a catastrophe. The phrase that everyone dies is not hyperbole. It is the unforgiving reality of vacuum exposure. Every entry and exit in space begins with trusting that the seal will hold. We are learning how to build with Martian dust. Transporting construction materials from Earth to Mars is prohibitively expensive, so scientists are developing ways to use local resources. Martian regolith, the dusty soil covering the planet, could be processed into bricks, concrete-like mixtures, or even 3D printed structures. Experiments have shown that certain binding agents or microwave sintering can turn loose dust into solid building material. Using local resources dramatically reduces the mass and cost of missions, while enabling larger-scale construction. Habitats, radiation shields, and landing pads could all be built from what is already on the ground. Research continues both on Earth and aboard the International Space Station to refine these techniques. The ability to build with Martian dust is a cornerstone of plans for permanent human presence. Every brick made on Mars is a step toward turning a barren world into a new home. People can lose their sense of direction forever in microgravity. The human sense of orientation relies on gravity pulling down and inner ear signals confirming which way is up. In microgravity, these cues vanish, leaving the brain confused about spatial relationships. Some astronauts adapt quickly, while others struggle with persistent disorientation throughout their missions. Research suggests that long-duration exposure can cause lasting changes in vestibular function. Upon returning to Earth, recalibrating to gravity can take days or weeks. In extreme cases, some individuals report ongoing difficulties with balance and spatial perception. The experience is more than uncomfortable. It highlights how profoundly our senses are tuned to Earth. Engineering solutions like visual cues and consistent module orientations help crews maintain a sense of up and down. Losing direction in space underscores the hidden adaptations our bodies require to live beyond our home planet. You can watch lightning storms from above. From the International Space Station, astronauts have a unique view of Earth's weather, including thunderstorms that flash with brilliant lightning. Looking down at night, the glow of electrical discharges illuminates cloud tops in dramatic flickers. Some lightning reaches upward into the atmosphere, creating phenomena known as sprites and jets that are rarely seen from the ground. Observing storms from orbit provides valuable data on atmospheric electricity and severe weather patterns. Photographs and videos captured by astronauts have contributed to meteorological research and public education. The perspective transforms something familiar into a spectacle, witnessing the raw power of weather from a vantage point few will ever experience. Watching a storm pass beneath you is a humbling reminder of the dynamic forces shaping our planet. Lightning from above is one of the many visual wonders astronauts treasure. There is no natural fresh water anywhere except on Earth. Across the known solar system, liquid water at the surface is extraordinarily rare. Mars has ice and possibly subsurface brines, but no lakes or rivers of drinkable water. Europa and Enceladus harbor oceans beneath icy crusts, but accessing them would require drilling through kilometers of frozen shell. Comets and asteroids contain water ice, but it is locked in solid form amid rock and dust. Earth's abundance of liquid fresh water, flowing in rivers, filling lakes and falling as rain, is unique among known worlds. This makes our planet an oasis in a cosmic desert. Water recycling is mandatory for space missions, precisely because there is nowhere else to get more. The search for water drives much of planetary exploration, since it is essential for life as we know it. Appreciating Earth's water requires understanding how precious and rare it truly is. The first human footprint on Mars will change everything. When a boot finally presses into Martian soil, it will mark a turning point in human history comparable to the first steps on the Moon. That moment will prove that humans can survive the journey, endure the landing, and walk on another planet. It will inspire generations and open debates about colonization, terraforming, and what it means to be a planetary species. The scientific and cultural significance cannot be overstated. Every challenge overcome to reach that footprint will validate decades of research and investment. The image of that print will become iconic, studied, and celebrated for centuries. It will also raise new questions about responsibility, governance, and the future of Mars. A single footprint on the red planet will divide history into before and after. Everything that follows will be shaped by that first impression in the dust. Spacecraft computers must survive cosmic radiation. Electronic circuits are vulnerable to high-energy particles that can flip bits, corrupt data, or cause permanent damage. Spacecraft computers are built with radiation-hardened components designed to withstand the harsh environment of space. Redundancy is key. Critical systems often run on multiple processors that cross-check each other's calculations. Memory is protected by error-correcting codes that detect and fix single-bit errors automatically. Despite these precautions, intense solar events or passage through radiation belts can still cause disruptions. Engineers plan for inevitable anomalies and design software that can recover gracefully. The challenge intensifies for missions beyond Earth's protective magnetic field. A computer failure in deep space could strand a crew with no hope of rescue. Building reliable electronics for the void is a constant battle against invisible adversaries. Future astronauts might hibernate on the way to other planets. Long-duration spaceflight poses enormous challenges for life support, food storage, and crew psychology. One proposed solution is placing astronauts in a state of torpor, a controlled reduction in metabolism similar to hibernation. Lower metabolic rates mean less food, water, and oxygen consumption, reducing payload mass significantly. Psychological strain would be minimized if crew members essentially sleep through the months-long transit. Research into therapeutic hypothermia and metabolic suppression is exploring how this might be achieved safely. Animals that naturally hibernate provide biological models for understanding the process. While human torpor remains experimental, its potential benefits for missions to Mars and beyond are compelling. Waking up months later at a distant planet would turn science fiction into reality. Hibernation could be the key that unlocks truly long-distance space travel. You can see the aurora from space as glowing rings around the poles. From orbit, the aurora borealis and aurora australis appear as luminous curtains and rings encircling Earth's polar regions. Charged particles from the Sun interact with the magnetic field and atmosphere to produce these stunning displays of light. Astronauts have photographed the aurora in vivid greens, reds, and purples, capturing images impossible to see from the ground. The glow extends far higher than it appears from beneath, reaching altitudes of several hundred kilometers. Watching the aurora from above reveals its true scale and structure as a dynamic, shimmering crown. Solar storms intensify the displays, sometimes extending the aurora toward lower latitudes. The phenomenon is a beautiful reminder of Earth's invisible magnetic shield at work. Seeing the aurora as glowing rings is one of the most awe-inspiring sights astronauts describe. The journey to another star may take generations. Even the nearest star system, Alpha Centauri, is over 4 light-years away, an almost incomprehensible distance for current propulsion technology. A spacecraft traveling at the fastest speeds we have achieved would take tens of thousands of years to arrive. Proposals for interstellar travel include generation ships, massive vessels designed to sustain entire communities for centuries as they drift between stars. People born on such a ship might never see their destination. Their descendants would complete the journey. The cultural, ethical, and psychological implications of multi-generational voyages are staggering. Alternative ideas like embryo ships or digital consciousness transfer raise even more profound questions. For now, the stars remain tantalizingly out of reach, but dreamers and engineers continue to plan. The journey to another star will test everything humanity thinks it knows about identity, purpose, and time itself. And now, the quiet wonders of space travel begin to gently fade into the stillness of the night. You have wandered through over 100 peaceful truths about the vast cosmos beyond our world. From the first moments of liftoff to the silent drift through the void. From astronauts learning to sleep strapped to walls to tears that float like tiny spheres. From the bone-deep challenges of living without gravity to the haunting beauty of watching Earth from orbit. You have explored how spacecraft protect us from the vacuum, how bodies change in weightlessness, how time itself bends when you travel fast enough. You have learned that beyond every sky you have ever seen, there are countless more, all stretching into infinity, all waiting to be explored. You are connected to this story more deeply than you may realize. Right now, as you listen, satellites are passing overhead. The International Space Station is circling the planet. Distant probes are drifting through the outer reaches of the solar system, carrying messages from Earth into the unknown. The universe does not need your attention. It simply exists, vast and patient, as it has since the very first moment of creation. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady, like the gentle orbit of a spacecraft around the Earth, like the quiet hum of life support systems keeping astronauts safe through the long night. Tonight, as you rest, the cosmos continues its quiet work. Stars are being born in distant nebulae. Planets are turning on their axes. Light from galaxies millions of years away is only now reaching your sky. And somewhere, perhaps, another curious soul is looking up at the same stars, wondering what lies beyond. You are a small, warm presence within this vast universe, peacefully resting among the wonders. Sleep well, sweet dreams, and may you carry with you the quiet knowledge that you are never truly alone, for the stars are always there, burning, turning, and watching over you in ways you will never fully see. Thank you for joining me on this journey through the mysteries of space travel. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of how our universe works. There are more wonders waiting. More secrets hidden in the depths of space and the quiet corners of distant worlds. More gentle truths to drift through on quiet evenings. Rest well, and may the gentle light of distant stars keep you company through the night. This has been Drowsy Discovery. Good night.